How to Cook Cisco, George Nosenko. En esta charla nos contarán detalles técnicos de la vulnerabilidad que George Nosenko encontró mientras investigaba tocando temas como DEP Bypass Technique, Roping, cómo deshabilitar el servicio DEP, Omelette Hunting, Cisco Code Integrity Mechanism Bypass y cómo desarrollar una consola para PIC en lenguaje C, y promete que si después de todo esto queda algo de tiempo, nos contará sobre la vulnerabilidad en sí misma. George Nosenko es un investigador de seguridad y desarrollador de explotaciones en la empresa Embedded. En el pasado, encontró muchas vulnerabilidades en productos de SAP, HP, Oracle, Avast, Bitdefender, Cisco, entre otros. En 2017, ganó el premio G-Influence en Gitpong Hong Kong 2017 por su exitosa explotación de vulnerabilidades en Cisco iOS.
Hello everyone, it's good to see you all here. Let me introduce myself. My name is George. I'm a bug hunter, reverse engineer, and export developer at Embedded company. In my talk, I will tell you about Cisco exploitation. I'm going to describe the steps to execute arbitrary code in Cisco iOS according all the relevant mitigation to given moment. These steps reflect both our own experience, Cisco exploitation, and experience of other researchers. Successful Cisco exploitation depends on the context of vulnerability and a particular device. So consider all these steps as a set of recipes and not complete solution. So let me first give you a brief overview of milestones Cisco exploitations. The exploitation of Cisco dates back earlier O's, about 15 years ago. It was marked first cases of buffer overflow and heap overflow exploitation. Due to the Cisco iOS specific and features and traits, the exploitation of this system requires to develop new approaches and exploit techniques. In the following years, researchers' major efforts were aimed to addressing the Cisco diversity problem, mass exploitation Cisco devices. In particular, there were introduced several approaches to implement the shellcode that could be transferred between different devices. Speaking of the latest notable events in the world of Cisco exploitation, we should mention two exploits for Cisco ASA appeared in 2016. The first one, EKE exploit for CVE 2016-1287 that became the winner in the Pawnee for best server-side bug category. The second one, Extra Bacon, is one of the NSA tools. It exploits the vulnerability in implementation of SNP protocol. In this year, CIA Vault 7 leak occurred. The leaked information included a description of ROSM tool, an exploit for vulnerability in cluster management protocol. Later, Cisco announced that this vulnerability was fixed, but a few months after this, Artem Kondratyenko rediscovered the very same vulnerability and made a one-day exploit for it. The exploit uses the rope technique to get access with the highest possible privilege via Telnet. The world of Cisco devices from is indeed extremely diverse. There is a good deal of network equipment, models, and several proprietary operation systems that can be based on different types of CPU architecture. Each of them is unique. It proves to be quite a challenge to write an exploit that would work even within one OS family. That is why when we're speaking about Cisco exploitation, one should specify what particular device contains a vulnerability in the question. In our research, we choose affordable and widely spread model, Cisco Catalyst 2960 switch. This device is based on the processor of the PowerPC 405 and run on Cisco 12.x or Cisco iOS 15.x. Cisco, without discussing a specific device, Cisco iOS has the following features that affect exploitation. Cisco iOS is proprietary software, so it means that exploitation can be done without reverse engineering. An image is a single unit, a large statically linked binary. The whole code is executed in the privileged mode, which is quite a good news for us because it makes it possible to use privileged instruction. The process shares the same virtual space and therefore are not protected from each other. The scheduler uses non-preemptive multitasking. It means a task chooses a moment to return CPU time on its own. Another important feature of Cisco iOS is its behavior in case exception. If something goes wrong, Cisco iOS will reboot the device. There is no open API for third-party developers, which complicate exploitation because an exploit developer has to search address for all the interesting functions. The major part of our research is based on real experience zero-day exploitation we demonstrated during contest Geek Poland 2017. The detailed information about the vulnerability will be disclosed after a patch is released. For now, we can only say the vulnerability is a stack buffer overflow that takes place when a malicious network packet is processed. Before we start exploitation, let's find out what mitigation are there in Cisco iOS. Sure, some of listed mitigation are not mitigation in full sense of the word, but still they do complicate exploitation. Data execution prevention. Stack, heap, EO memory are not executable. Stack and heap randomization. Check heaps. These security mechanisms specific for Cisco that perform a series of actions to check heap integrity once a minute and when the memory is released or allocated from heap. Note, in Cisco iOS, a stack is located in heap, so it's likely that you will have to deal with this mechanism even if you try exploiting a stack-based overflow. Code integrity checking, it tries to prevent a code modification. Watchdog timer. If your shellcode works for a long time, The watchdog timer will be triggered and will interrupt the exploited process. Cisco diversity. It hampers mass exploitation. iCache, Dcache on PowerPC, it makes it more difficult to modify code and to pass control to data region. To execute an arbitrary code, first you need to gain control. For this, you can use buffer overflow or heap overflow vulnerability. After that, you must bypass DEP. Then need somehow to solve the too many cache problems. Next, if you are going to modify the code, you will have to bypass check integrity mechanism. After, you write and execute your payload. Finally, you must terminate the shellcode so that it does not cause the device to reboot. Now, let's consider one each step. But before, let's little speak about debugging. It's necessary for each step of exploit development. For at least 15 years, it has been possible to use GDB kernel commands to debug Cisco iOS. But new images no longer have this command. Fortunately, we managed to find new way enable debugging in some models. You can see this way on this slide. For debugging, you can use IODID tools by NNC group. But be careful, some mitigation are disabled in debug mode, so test your exploit without debugging at every step. Okay, gain control. So first step on the list is to gain control. If you have a stack buffer overflow, it's plain and easy. You just overwrite a return address. If you have heap buffer overflow, you will be able to transform it to write for primitive. And you have a lot of function pointers to override. A few words about the structure of the stack frame. Here you can see the stack frame and instruction to closing it. In PowerPC, a return address is stored in LR register. The address of the top of the stack is stored in R1 register. By now, you have gained control, and you must bypass DEP. To do it, you have used well-known code reuse attack, rope. There are several options. First one, you can try to write rope-only shellcode, or make write for primitive to overwrite important code or data, or somehow disable DEP and execute generic rope, or generic shellcode, no rope shellcode. As I said above, rope is a well-known exploitation technique. Therefore, I'm going to talk only about the features of rope related to PowerPC and Cisco iOS. It's quite possible you would have too little space in the stack to put your rope chain, because if you write too much data, you will corrupt heap metadata, and the check heaps mechanism will reboot a device. While a rope gadget consumes a lot of space on stack, good example of this, the gadget on the slide. It just copy value from R22 register to R3 register, but this gadget consumes 80 bytes. A few words about tools to finding gadgets for the PowerPC. ROPA is good tools, but it misses some types of useful gadgets. So that is why the PPC gadget finder script for IDA Pro came into existence. It let find you a wider range of useful gadgets. You can download these from our GitHub. Let's now take a look at a brief catalog of gadgets that may be useful for exploitation. The first one is write-for primitive. It's a very powerful gadget. It allows overwrite any code and any data. Due to the calling convention used for the C code compiled for PowerPC, it's rather complicated to find gadgets that load a value from stack to the R3 to R17 registers, which you should certainly do, for example, to pass arguments to a code function. You can initialize a register with small numbers using several gadgets, but this will increase your chain. Still, there is a better solution. Use the BLRL gadgets. Take a look at these gadgets take a look at the gadgets on the slide. It loads a value from stack to R5 register, and at the same time, it doesn't consume extra space on the stack. In order not to break the rope chain, you should, in the previous gadget, load to register R27 address of next gadget that must update our register. It might be necessary to call a function from your shellcode. For example, memcopy function, or pass control to the second stage shellcode. To do this, you can use these gadgets. There are gadgets that enable execution of several actions, thus saving space on the stack. Here, one example of these gadgets, it can perform 3 actions at the same time. It's convenient when you need to initialize a large number for register, for example, to pass arguments to Omelette Hunter or second stage shellcode. Here's another couple of useful gadgets. The stack keeper gadget allows saving a pointer to the stack, which is quite convenient, while it will point to our shellcode. The debug gadget is useful for debug purpose. Basically, if the context of vulnerability allows, then you can create an exploit using only gadget above. But in general case, the final goal is to execute arbitrary code. And for this, it's necessary to disable deb. What do we have? There are not API like Virtual Protect or mProtect, but you can try to abuse PowerPC memory management unit. How does deb work on PowerPC? deb is part of virtual management system. The effective to real address translation uses TUB entries. A TUB entry describes a memory region including access control information. To set up a TUB entry, you should use special instruction and registers. Note, the address translation flow, structure of TUB entry, and the TUB management instruction depends on PowerPC family. As I said earlier, Cisco Catalyst 2960 uses PowerPC 405. You can see a structure of TUB entry for this CPU on this slide. Here's an excerpt from datasheet. For us, the access control fields are important. EX bit, when set, enable instruction execution at addresses within a page. ZPR setting can override that. VR write enable bit when set enables story operation to address within a page. ZPR setting can override that. The fact that ZPR register can override the permission sounds promising. What is this ZPR? Let's figure it out. ZPR is designed for flexible and effective work with pages protection. The ZPR field bits can modify the access protection specified by TLB entry. The real value of field define how the protection is applied to all pages that are member of that zone. Thus, if you could write value 3 to one of the fields ZPR, then we would assign execution and write permission for a zone. That would be great if we can find a gadget that changes the value of ZPR register. And yes, we can. Such gadget can be easily found by this binary pattern 7C10EBA6. At closer look, you will see that there is a problem with it. After writing the value to ZPR register, value from R11 register is written to MSR. MSR is a machine state register. It's very important. You cannot write an arbitrary value there. In this case, the processor will go to an undefined state, most likely the device will be reboot. What can be done about this? Let's consider the whole function. You can see that at the beginning of the function, the current value of the MSR register is stored. Then the new value of ZPR is read from a global variable gZPR value. Thus, it's obvious that you can solve the MSR problem if you call the enter function. But this will require the initialization of the variable gZPR value. For this, you can just use write for Gadget. In order to make it perfectly fits a great multitask gadget. After execution, this multitask gadget in ZPR register, the value of FFFFF will be written, which will allow execution in any of memory regions and also allow write in the memory area containing the code. So, another family of processors that are put into Cisco equipment is the PowerPC E500. What about these models? There is not anything that looks like ZPR. To manage the TLB entry, mass register are used. For us, the MATH3 register is important. It contains access control field. UX, SX, UW, SX bits enable execution and write in memory region. Using the same binary pattern that was used to find the DEP disable gadget for the PowerPC 405, you can find gadget that disable DEP on the PowerPC E500. It's very convenient that these gadgets allow you to load all necessary values directly from the stack without using additional gadgets. Excellent. Now you can try execute generic shellcode. But for this, you have to solve a couple problems. As mentioned above, you will most likely be very limited in space on the stack. In addition, most of it's occupied by the rope chain. The second problem is that passing control to the stack will cause the device to reboot because of instruction and data caching. To solve the first problem, you have to use a multi-stage shellcode. And to solve the second problem, you should disable or invalidate caching. When you're writing a multi-stage shellcode, you need to answer the following question. Where should we look for the second stage shellcode? There is two options, heap or I/O memory. Where should we move the second stage shellcode? We can move shellcode in text section, code section, or data section. What do with the caches? We can try to disable cache or try to invalidate cache. To answer this question, we'll have to develop an egg or omelette egg hunter. If you are lucky, you will be able to find the shellcode on the heap, but it may happen that the buffer will be released. An alternative is searching your I/O memory. I/O memory is shared memory that's visible for both the CPU and media network controllers or a data bus. Network packets are stored in a double linked list of packet data structure located in the carrier dump I/O mem region. The structure of packet data depends on the version of Cisco iOS. This should be taken into account when developing Omelette Hunter. If the shellcode is large enough, you will encounter a fragmentation problem. That is, your shellcode will be distributed over several packets. What can we do about this? It will be necessary to collect the shellcode in parts. To find all the parts and collect them, you can use information from IP and TCP headers. At this moment, we figured out how to find the shellcode and collect in parts. It remains to solve the problem with caches. You may not be able to disable caching as suggested in previous research. For example, in our case, on Cisco Catalyst 2960, the code containing a function to disable the cache was not available at the time of exploitation. But we found a function, iOS move handler, that copies the code of the interrupt handlers during the initialization process. This function moves the data and immediately invalidates both caches. Where to move our shellcode? Consider the case when we will rewrite a code. Because it looks more reliable than other options, this case is also interesting in that it's applicable if you need to modify Cisco iOS code. For example, if you want to hook some function. Now we have all the components to create an Omelette Hunter and collect next stage shellcode. You can download Omelette Hunter this Omelette Hunter for our GitHub. In the last step, we decide to rewrite the code. But we just cannot do it because of in Cisco iOS has a mechanism, checking mechanism that check integrity of code in memory. This mechanism is part of check heaps mechanism and periodically calculates the checksum of the code in memory. And if the code is modified, it reboots a device. It can be assumed that this mechanism was created against exploitation techniques and implants which modify code. You have several ways to bypass this mechanism. Instead of the code modification, you can modify data. Checksum algorithm is very simple, so you can add some extra byte to correct checksum. You can bypass integrity checking by modifying global data, for example, compile time checksum, current checksum value is the bug flag. The last option is you can use free space between regions. The last way looks more attractive due to the simplicity of implementation and the lack of binding to offset in image. If you look at checksum function code, you see that checksum is calculated from the address start of code to the address end of code. In our case, start of code is equal 3000 and end of code equal is to 01, 71, 52, 33. If you look at the memory map, you will see that between region code query dump text and region DO text, there is a space uncontrolled by the mechanism of code integrity. So we have about 939 kilobytes to place our code. Now it's time to talk about payload. Whatever shellcode you decide to implement, we recommend that you develop it in C language. This simplifies the development of large shellcode and makes it portable to other CPU architectures. Especially for this, we have developed a template for shellcode which you can download from this link. This template uses GCC to build position-independent code for PowerPC and simple assembler code to fix global offset table. Due to the lack of an open API interface and Cisco diversity, your shellcode will only work on one image of the device if you don't make an effort to avoid it. Explore the materials on this slide to choose an approach to create an image-independent shellcode. Each of them offers an invariant to overcome Cisco diversity. After your shellcode does everything that was required of it, you need to think about its correct completion. The option of completion depends on the type of shellcode and the vulnerability itself. Sometimes it will be enough to return control to a column that code a vulnerable function. This is a pretty good option since it does not depend on a particular image. Of course, yes, you clean up. If you can clean up. In other cases, it will be more convenient for you not to return control at all. For example, running an infinite loop at the end of shellcode, but this will cause you have to deal with a watchdog timer. As already mentioned, Cisco iOS uses cooperative multitasking in order to prevent the capture by any process of all CPU time. In Cisco iOS, the interrupt from the timer runs code that terminates the process that has been running for too long. This makes you take care of your shellcode to work as fast as possible or give sometimes CPU time to other processes. Let's consider one of possible way to return process time to other processes in image-independent manner. You can use the tickle sleep function. As you can see in this screenshot, it calls inside self process sleep 4. You can find SQL sleep address during the execution of shellcode. This method used in template shellcode, the link of which was given above. First, let me show you a concrete step which will done to execute arbitrary code execution at gig power. First, we gain control by return address overwriting. After that, our rope chain bypassed DEP and moved omelet egg hunter to space between the code regions and then transfer control to it. Then the omelet egg hunter collects SQL shellcode, and moves it to a code area that is not under control of integrity checking.
A small interruption
Okay.
from the conference. I assume you drink vodka, right?
No, I don't. I don't drink alcohol.
Like that.
No. No. Oh.
But that's for me.
Oh.
A big applause.
Cheers. Thank you very much. It's helped me relax.
Yeah, that's the spirit.
Oh, so then the omelet egg hunter collects SQL shellcode and moves it to a code area that is not under control integrity checking. Copying occurs with a cache invalidation. Next, the shellcode runs the reverse SQL server, which executes commands received over a network. For shellcode completion, an infinite loop was used. Let me show you this demo. In this case, we will get full control on the switch. Now we check, we have a switch and can connect via Telnet, but we doesn't know password. So we try to exploit it. Now we run command server. Никто не видит. Sorry. Can you help me? Okay, thank you. Okay, sorry. We have a switch. Now we try to connect to it via Telnet, but we doesn't know a password, so exploit it. We run a command server. Specify our current IP address. Okay. Now we run exploit. We pass as parameters IP address of target, current IP address, and the name of file and the file name of the second stage shellcode Okay, export, well, work, well, good. No, there are several macro commands. We can check our privilege level is highest. Now we can collect information about neighbors. Can show and modify config file. So get some credential. Let's set new user with name hacker. Now we unlock, change password to enter privileged exec mode. Okay, so try to connect switch with new credential. Okay, it's work. Now type enable password. No. Enable password. Yes. We can enter to privileged exec mode and execute any command. For example, we can rename switch name. Thank you. Thank you very much. Okay. In the second case, we will intercept traffic between a client connected to switch and internet. Now we'll run export as last time. Okay, now we redirect all traffic from victim to our interface. For this, we specify a source interface name and the destination interface name. Check that everything is right. It's okay. Now we run tools, DriftNet, to intercept all pictures from victim. Okay. Now we on client side and go to our site, dev version for which HTTPS was disabled. You can see that all pictures was intercepted. That's all. Conclusion. Cisco iOS is quite well protected from exploitation, and an arbitrary code execution for Cisco is not a trivial task, but still feasible. I hope that you find this work useful and interesting for yourself, and I'm sorry for my English. It's really bad. Thank you for attention. you.